Harnessing Nonlinearity, Part 5, Perturbation Theory. Since its inception, the foundational theory of motion in circular particle accelerators has been built around linear dynamics. The celebrated Courant-Snyder theory, developed in the 1950s, provided a powerful analytical framework for understanding phase-space evolution in systems weakly perturbed from harmonic oscillations, forming the theoretical backbone of modern accelerator design. However, this linear formalism is increasingly strained in the face of modern challenges: higher beam intensities, smaller beam impedances, tighter stability margins, and the pervasive presence of nonlinear magnetic elements in advanced accelerator facilities, such as the Integrable Optics Test Accelerator IOTA, as well as in proposed next-generation machines like the Muon Collider or the FCC. Despite the critical role of nonlinear effects in determining long-term stability and beam quality, a general analytical extension of the Courant-Snyder formalism to strongly nonlinear regimes has remained elusive. In this final tutorial, we present such an extension: a systematic perturbative framework for constructing approximate invariants in symplectic reversible maps. Prominently, this method is compact both in formulation and implementation, relying on a single guiding principle: approximate invariance. In the integrable case, an exact invariant K exists and satisfies condition where right-hand side is equal to 0. We generalize this to non-integrable scenario by relaxing the right-hand side to allow deviations of order n+1, where n defines the order of perturbation. From this single condition, we construct a parametrized function that captures the essential geometry of phase space, revealing the topology of nonlinear motion, the structure of primary island chains, separatrices, and the amplitude dependence of the rotation number. Consider a symplectic map of the plane T, meaning it preserves both area and orientation, and that admits a power series expansion. For model lattices with thin lenses, such a one-turn map can be easily constructed using modern mathematical software. For more realistic accelerator lattices, virtually all accelerator physics codes internally represent the system as a series expansion before proceeding with iterations. We begin our perturbation theory by introducing a general polynomial n-sets for an approximate invariant of order n, written in terms of sum of homogeneous polynomials Km of degree m+2. To determine the two indexed coefficients C, we impose the condition that the approximate invariant is conserved up to the order of epsilon to the n+1. The deviation from exact invariance is referred to as the residual, denoted with capital R. The lowest order contribution, which can also be obtained via standard linearization, is defined only up to a constant multiplier C0. This is called the seed coefficient, and it can be set to unity or adjusted specifically to eliminate resonant denominators. However, this is not the only source of underdeterminacy. Even after all two indexed coefficients are fixed, the invariant remains underdetermined up to an additional series involving single indexed coefficients. Nonetheless, the approximate invariance condition still holds to the desired order, and the twist coefficient tau k converges at order n equal to k+2. The remaining coefficients ck are obtained through an averaging procedure that minimizes the residual error. After transforming the map to the eigenbasis of its Jacobian, the linear part becomes a pure rotation. The level sets of the zeroth order invariant are then circles, suggesting a natural transition to polar coordinates in phase space. Since the residual is a periodic function of the polar angle, its average over an initial phases vanishes. However, to optimize the approximation, we instead minimize the integral of its square. This leads to a new linear system whose solution yields the coefficients ck. Let's now see how the perturbation theory we discussed can be used to build on the foundational formalism developed over 70 years ago by Ernst Courant, pictured on the left, and Hartland Snyder on the right. Recall that in accelerator physics, The linear theory of motion relies on a parameterization involving the coefficients alpha, beta, and gamma, collectively known as the Courant-Snyder or twist parameters. These parameters are not all independent. The symplectic condition imposes a constraint that allows one of them to be eliminated. Also, by convention, the beta function is taken to be positive. The phase advance phi, defined as 2 pi times nu 0, corresponds to the Betatron phase per turn. This parameterization allows quick, linearized estimates of several experimentally important quantities. First, the Betatron tune nu 0, representing the frequency of horizontal or vertical oscillations around the reference orbit, or the synchrotron tune in the longitudinal case. Next, the Courant-Snyder invariant, which provides a compact representation of phase space trajectories at a fixed location in the accelerator. By propagating the twist parameters along the machine, this invariant allows the reconstruction of motion not just turn by turn, but also continuously along the ring's circumference. This same invariant can also be obtained through the perturbative method introduced earlier by choosing C0 equal beta star over A01, where beta star is the beta function at a reference point. Furthermore, this normalization of the invariant leads to a direct relationship with the beam emittance, which quantifies the phase space area occupied by the beam. Emittance is a key figure of merit in applications ranging from colliders, where it affects luminosity, to machines involving strong damping mechanisms such as muon collider or facilities using electron or optical stochastic cooling. The perturbative method naturally extends this linear framework. The zeroth order Courant-Snyder invariant becomes the first approximation in a systematic series. In many practical cases, low-order approximations already provide sufficient accuracy for describing the dynamics, as we will demonstrate later. Moreover, the approximate invariants can be rescaled to match the action, yielding a nonlinear analog of emittance, just like in the linear theory. Similarly, the linear tune nu 0 can be generalized to its nonlinear analogs derived directly from the invariant. Finally, notice that the transformation to the eigenbasis required for the averaging procedure is achieved via the well-known Flaquet transformation and is associated Betatron amplitude matrix. Once the coefficients Ck are computed, they can be substituted into the non-averaged invariant, written directly in physical coordinates, making the method especially suitable for experimental use. One important question remains: how do we obtain nonlinear approximations to the Betatron tune? The answer is, we extract it from the approximate invariant. Fortunately, this problem was addressed by Slava Danilov, who formulated a theorem enabling the direct computation of the Poincare rotation number from a given invariant of motion. This theorem is highly geometrical in nature and, at low orders, yields exact analytical expressions, often involving Jacobi elliptic functions and elliptic integrals. For higher order approximations, it remains practical via numerical or semi-analytical methods. For a detailed proof and generalization to higher dimensional systems, we refer the interested viewer to the two papers shown below. It is worth noting that this series of approximations is distinct from the traditional twist expansion. However, a comparison shows that for each even order n equal to m, the coefficients tau 0 through tau m-1 in the twist series converge to the exact values within this perturbative framework. Now, let's turn our attention to a series of figures that illustrates this method for several circular accelerators at Fermilab, which differ significantly in both design and purpose. Third integer resonance slow extraction in the delivery ring machine for the mu2e experiment, panels A1 and A2. The integrable test optics accelerator, also known as IOTA ring, panel B, and the main injector ring, panels C1 and C2. In each case, we use the full machine map, including all nonlinear thin or thick elements derived from a lattice file describing magnet locations and strength. just as in each standard accelerator simulation code. We compare direct numerical application of the map, black dots, with the level sets of the average approximate invariant shown with red curves. Each red curve corresponds to the trajectory seeded by the matching black point. If a red curve is not visible, it is fully overlaid by the trajectory, emphasizing the excellent agreement. In examples A1 and A2, dynamics are dominated by a singular third-order resonance, and even a low-order approximation, n equal 4, corresponding to action squared, by the way, gives outstanding agreement. In the iota ring, we observe a non-singular third-order resonance dominated by octupole-type nonlinearity and characterized by a distinct chain of 3 islands. In panel C, the main injector ring exhibits high-order resonances and chaotic behavior, but even a 6th-order approximation, n equals 6 or action cube, accurately captures the stability region and general structure of the phase space. Finally, we stress that the examples shown rely on unrefined bare lattice configurations, which include imperfections and design features not yet resolved or optimized experimentally. These cases often prompt direct simulations aimed at improving performance, as in A1 and A2, or reducing determinal resonance structures, as in C. That our method performs well in such cases underscores its value as a robust and complementary tool for nonlinear dynamics analysis. While previous examples demonstrate the power and versatility of our method through the applications of 3 distinct accelerator rings at the Fermilab, it is important to comment on limitations and potential extensions. First and foremost, this method is not intended to replace traditional simulations during the final stages of machine design, where collective effects must be accounted for. Nevertheless, even in such regimes, it offers critical insight into intrinsic single-particle dynamics, such as amplitude-dependent tune shifts, which are essential for estimating instability thresholds and determining the level of Landau damping, which is required for instability suppression. While the next natural step is a generalization to higher dimensions, we see that even a 2-dimensional analysis often yields remarkable value. This includes a range of practical scenarios such as accelerators with flat beams, where the horizontal beam size is much larger than the vertical. Then, systems dominated by a strong 1-dimensional resonance, as in the case of the main injector. Next, machines designed to exploit nonlinear instability for slow resonant extraction, such as the mu2e delivery ring. Finally, round beams, where this method can be directly applied to radial degree of freedom. For those interested in exploring these details further, I encourage you to consult the referenced articles. They offer a deeper dive into both the theoretical foundations and practical implementations of this perturbative framework. Thank you for your attention, and I look forward to any questions you may have.